Hello mates, in the previous video we talked about satellites, and I said in the next video we're going to talk about special satellites called geostationary satellites or geosynchronous satellites. As the name suggests, geostationary, they are stationary with respect to the geography or to the earth, or geosynchronous as in they are in synchrony with the what? With the geo or with the earth. That's what you can deduce from the names, but let's see the mathematics behind them. So, or the definition, the proper definition is it's a satellite that stays above the same point on Earth. That's basically what a geostationary satellite is. Imagine this is Earth, right? Imagine this is Earth. If this one is Earth, and then we have a satellite at this point here. We have a nice satellite at that point. If that is our satellite that is above this point, yeah, imagine that satellite is above that point. Let's say this satellite is spying on what? On the Witt's Great Hall. Let's say that's what it's doing. This satellite is always spying the Witt's Great Hall. It's on top of the Witt's Great Hall. Now you know the Earth rotates every day, isn't it? So this Earth is going to rotate. But can you see what the satellite is doing as well? It's staying on top of Witt's, spying on the Great Wall, no matter how the Earth is going to rotate. Even if the Earth is going to rotate in this way, it's still, okay, that hasn't happened, but if the Earth is going to go back and forth, that geostationary satellite stays on top of the Great Wall every time. So that's basically what the geostationary satellite, it's stationary with respect to geo, or it's in synchrony with respect to the Earth. We are going to see this synchrony part now using mathematics. So these particular satellites, I just gave an example of it, but these satellites are only possible if they are above the equator. So which means we have to move VITs to the equator for this to be possible. But they are what? They are only possible above the equator. Such satellites are used for TV, radio transmission, weather forecasting, and all. It makes sense because otherwise, if this satellite was moving faster than the Earth, maybe it's here. The signals would not go to the same place, because imagine we had a tower here and another tower here, the receiver at this point. If this receiver sends out signals, it will send signals to this satellite expecting it to be there, and then this satellite will send out signals to your home here. But imagine if this satellite wasn't at the same point above the Earth. Imagine after 5 minutes it's now at this point. It means this signal that is being sent here, it's already lost. It will get lost in space. It will get lost in space, and it will no longer come to this receiver here, and we lose signal up until the time when this satellite is back to where it's supposed to be here. When it goes around, when it comes here, we see some TV, some soccer or whatever that you like. I personally like American football, and then I see American football here. But then when it moves, I don't see it. So which means I have to wait for it to come back to the same position. So these are very important for TV, radio transmission, weather forecasting, and communication as well. So their periods are exactly. So now let's consider their periods. What's special about them? What's special about this is their periods are exactly equal to the period of the Earth. They're exactly equal to the period of Earth. Why? Because as the Earth is rotating, when the Earth rotates about its axis, it takes 24 hours. It takes a period for it to rotate right round, isn't it? But if this thing is always at the same point, then it means it's also taking 24 hours for it to remain to return to the same point. Imagine this orientation like this. This orientation like this. If it's going to take 24 hours to go right round, I don't know if you can see what I'm trying to achieve here. If it takes the Earth to take 24 hours to return to the same orientation, and the satellite is always at the same position, it means the satellite has also taken 24 hours to return to the same position. So the period is equal to the period of the Earth. So this will be equal to 24 hours. And with period, you can calculate most things. Since t squared is equal to 4 pi squared r cubed over GRE squared. That we proved that in the what? We proved that in the previous video. Therefore, I can calculate my R as equal to the cube root of T squared GRE squared all over 4 pi squared. And with that T I have, G acceleration due to gravity I have, and my R I have, my RE I have, 4 I have, pi was programmed in the calculator, so you don't even need to worry about that one. You get your R is equal to 42,400 kilometers. So what does this mean? This basically means that is the radius of the orbit of the geostationary satellite. So all geostationary satellites, they approximately orbit in a radius that is in this range. That is their range of orbit, which means from the center of Earth, their orbit will be 42,400 kilometers. That is their radius orbit. But you can calculate their distance above the surface of the Earth as the radius, the entire radius orbit minus the radius of the Earth. You get the what? This distance above the Earth's surface. That's what I'm basically calculating here. This is equal to 42,400 minus 6,400. You get that the height above the Earth's surface is 3,600 kilometers. And also with that, so this is the height above the Earth's surface. Also, you can calculate the velocity that they need to travel at in that particular orbit. It's what? It's 2 pi r over t. So this one will be equal to 2 pi multiplied by the radius of that orbit. The radius of that orbit, I'm putting big R, which is 42,400 over 24 times 3,600, just to put it in seconds. So this will be equal to 3.1 kilometers per second. So these satellites will be traveling at 3.1 kilometers per second for them to keep up with Earth, for them to remain at the same point always. So they have to travel at 3.1 kilometers per second. In the next video, we are just going to finish off gravitation with a section called weightlessness. After that, we would have finished gravitation. So stay tuned for that last video.